So now we're going to look at a specific example from Setter and Smith. Depending on the edition, it's example 10.4, 11.2 and 5 in the 7th edition, 11.3 and 11.6 in the 8th edition. And you have a 2-transistor amplifier with 2 MOSFETs, and we want to find the following characteristics: the voltage gain, the DC loop gain, and the output resistance using driving point impedance signal flow graph analysis. So first we're going to just take the circuit and draw the small signal equivalent. So here we have the transistors in the saturation region being replaced by controlled current sources. We are neglecting the output resistance RO of the MOSFETs. So we have GM1 VGS1 and then GM2 VD. The generation of the signal flow graph is easier if we show the difference voltage VGS1 as both VG, which is the same as VI, and VS1. That leads us to this diagram below. So we can see now the going down would be GM1 VG1, which is the same as VI, and then subtract, which means that it would go in the opposite direction, VS1, GM1 times VS1. So this is the diagram that we'll use, and now we can construct the signal flow graphs. We'll begin by drawing the node voltages. So just move over to the side and we'll start with drawing the node voltages. So we have VI, so we'll have 4 nodes. The voltage source VI. Then these 3 nodes in the circuit. So VD1, Vout, and VS1. Next, we will, remembering that the general form of the voltage is going to be a driving point impedance times the short circuit current. The next is then to draw in the driving point impedances of these 3 nodes. So the impedance, driving point impedance, is the impedance seen at the node with all other nodes grounded. So we can see for VS1, it's simply R1 in parallel with R2. For VD2, these are current sources, so they act as open circuits, so there's only RD1. And then finally, at the output node, you see RD2 and R2 in parallel. This would already be grounded, so we wouldn't see R1. There. So now that we have our impedances, we can look at the short circuit currents. Short circuit currents, then let's put them here. Associated with each node, then we have short circuit current for S1, short circuit current for the drain one, so D1, and the short circuit current for the output. Okay, so that these short circuit currents are then determined by looking at each node and then the currents that are going in, depending on the, assuming that that node is grounded, and then the other nodes are the transmittances from each of the nodes. So first, for VS1, then we see that this node, there's a current coming in, so that's equal to GM1 VI. So let's get GM1 VI. So that comes in as a GM1. Then another one coming out is GM1 VS1, but going out. So GM1 VS1, we're going to take VS1, and it's going to be GM1 but negative because it's coming out of the node instead of in. And then finally, there's a contribution from V out. If this is grounded, then it'd be V out over R2. So V out over R2. There. So that's VS1 done. Vn is just the input, so there's nothing to do. That's just a source. Then at the drain, we have two current sources again. So GM1 VI, but that current is coming out of that node. So it would be a negative GM1. We then have GM1 VS going into the node. So GM1 going into the node. And then finally we have, that node is done. So GM1, VD1, this node is done. Then finally the output node, we have the current coming out, that's equal to GM2 VD1. So that would be over here. Oops. And this is coming out of the node, so it's a minus GM2. And from this node VS1, it would be VS1 over R2. So we'll have VS1 over R2. And I'm going to just put this in orange over here, maybe a little bit thinner. So this is GM1 over R2. Okay. So there's our signal flow graph. Okay, just one correction. The short circuit current, the short circuit current at drain 1, I need to move this path over to there instead. So here it's just GM1 there. So this actually can go into here, and it is going in GM1. Okay, now there is the opportunity to simplify the graph, and I'll talk a bit more in a moment, but let's just take this graph and we'll simplify it. So to help us with the simplification, it's useful to look at the actual values of the different transmittance branches. So if we switched over, like in the CAD tool, to the numeric values, then the transconductances would be in milliamps per volt. So I'm just highlighting that it's milli. And the impedances are in the kilo ohms, so I'm highlighting that it's kilo with K. And a reminder that because the milliamps, you can have a consistent set of units if you use milliamps for currents, volts for volts, and kilo ohms. So we can actually just ignore the prefixes and then just multiply them out and you'll get volts. Okay, so this helps us to see then, for instance, that we can ignore 1 over R2, because 1 over R2 is basically about 1/9 is a little bit more than a tenth, so it's 0.11 milliamps per volt. And if we look at, compare that with the alternative path over here, so from VS1 to ISC0, you can go this way, or the alternate path this way would be 4 times 10 times minus 4, so that would be negative 160 milliamp per volt. So that's about over 1,000 times stronger path than this, so we could ignore this path and we can just take that out. The other one simplification is collapsing feedback paths back into its own node, and I'll talk a bit more about that in a moment, prove that. It's the source absorption theorem, but basically that tells us that we can eliminate this path by placing an additional component in parallel that's equal to 1 over the values that was GM1. Okay, so this is now a simplified version of the signal flow graph that we can move forward with to analyze. So now that we've made some judicious choices in simplifying the graph, we'll go ahead and calculate the first requirement, which is the DC gain, Vout versus Vi. So if we look at this signal flow graph, to simplify the expression, let's just replace all of the transmittances with variables A to H, okay? And then we'll just employ Mason's gain rule. So now we can just work with ABCs, and Mason's gain rule tells us again that the output, so the transfer function, Vout over Vi, is equal to the sum of transmittance paths. So we're going to have two forward paths from Vi to Vout. The first one is over the top here, so AEFG. So that would be one path, P1, A, E, F, and G. And we multiply that by its subdeterminant. So if you took away this path and you looked at the remaining of the graph, what loops there are, and you can see that there won't be any loops. The only loop in this signal flow graph is CDEFG. So let me just show you that forward path here. So going through here, so just mark path 1. This is path P1. And so you can see that once we strip this forward path out, it eliminates the feedback loop, and any feedback loops, and so the subdeterminant would just be 1 because there are no feedback loops, so it's minus nothing else. The second path is from the input to the output would be down through the bottom here, so that would be the second path out, and that would be P2, and so we would add P2, which is B, C, D, F, and G, and its subdeterminant, once you remove this path, again it removes the main feedback loop, and so the subdeterminant would also be just 1. So the numerator is just P1 delta 1, P2 delta 2 over the determinant, and the determinant would be given by 1 and minus the loop. In this case there's only one single loop, so around here this is our loop L, which is 1 minus C, D, E, F, G, and H. And hence the entire expression then would be A, E, F, G plus B, C, D, F, G over 1 minus C, D, E, F, G, H. And we would just substitute that expression if we wanted the algebraic expression. We can also, since we're only solving for DC, we want a numeric value, and we can just plug in the values for the letters. So now that we have the transfer function written out in terms of the different transmittances, we can either calculate a symbolic expression. In this case, to make it easier, I'll use the numeric values of each of the branches. So come over here, and then these are the numeric values, and so just plugging in all the values, we have then transfer function AEFG would be 700 plus 752. This second path, BCD, this is EFG, okay. And BCD EFG. So the EFG, that would be equal to negative. Remember here AEFG, there are two negative values, so the negative signs cancel. Going the other path, forward path, there's only one negative sign, so that's going to be minus 588.2, and that'll be over 1, and then minus CDEFG. Again, this there's a negative sign here, so it's going to be a negative value, and so that minus 16.35 then changes to plus, and the result is then 9.42, and that's going to be volts per volt, and that is what is expected from the example in the textbook.